Have you ever wondered how a tiny battery powers your torch or TV remote? What's really happening inside that little cell? Well, a cell is a device that converts chemical energy into electrical energy to drive an electric current in a circuit. In most low-voltage applications, it acts as the main power source. Now, here's a key idea. Every cell maintains a potential difference across its two terminals. This difference creates the push that drives the electric current through any external device or resistor connected to the cell. Inside the cell, there are two electrodes, a positive electrode marked as capital P and a negative electrode marked as capital N. These are dipped into an electrolyte solution which allows charges to move between the electrodes. And here's a relatable example. The battery in your flashlight or wall clock. It's converting chemical energy to electrical energy, just like that. Let's now zoom into what's happening at the electrodes. The positive electrode, capital P, acquires a higher potential. We denote this as V sub plus, meaning capital V with a subscript plus. The negative electrode, capital N, gets a lower potential, denoted as negative V sub minus or minus capital V with a subscript minus. The total difference in potential between the two electrodes when no current is flowing is what we call the electromotive force or EMF of the cell. It's represented by the Greek letter epsilon. The formula is epsilon equals V sub plus plus V sub minus, so even though the name includes the word force, electromotive force is not a force, it's a potential difference. This EMF represents the energy supplied by the cell per unit charge when no current is flowing. Now, let's talk about something that limits the performance of every real cell, internal resistance. When current flows through the electrolyte, the cell's internal components resist the movement of charge. This resistance is called internal resistance and it's represented by a small letter R. This internal resistance causes a drop in the voltage available to the external circuit. So when current flows, the terminal voltage is less than the EMF. The equation is capital V equals epsilon minus I times I here. Capital V is the terminal voltage, epsilon is the EMF, capital I is the current, and small r is the internal resistance. So, internal resistance results in energy loss inside the cell itself. And it's important to know, dry cells, like the ones used in household gadgets, usually have higher internal resistance than liquid electrolyte cells. So yes, your battery might still have chemical energy left, but its internal resistance could be too high to deliver that energy efficiently. Let's now see what happens when we connect a resistor across the cell, that is, when the circuit is closed. The current flowing through the resistor, denoted by capital I, creates a voltage across the resistor. According to Ohm's law, the formula is V equals I times R, or in words, terminal voltage equals current multiplied by external resistance. But now we must also include the cell's internal resistance. So, the EMF is related to both resistances by this equation, epsilon equals I times open bracket R plus a close bracket where capital R is the external resistance and small r is the internal resistance. So, the total resistance in the circuit is the sum of R and R, and this determines the actual current flowing. Let's compare two cases, when the circuit is open and when it is closed. In an open circuit, nothing is connected and no current flows. So, the terminal voltage equals the EMF, V is equal to epsilon, or in words, voltage equals epsilon. In a closed circuit, where current is flowing, some energy is lost due to internal resistance. Now, the terminal voltage becomes V is equal to epsilon minus I times R. This means the voltage available across the load is reduced because part of the energy is being used to overcome internal resistance. Real-world insight: to measure a battery's health accurately, You need to measure its voltage while under load, not just when idle. Let's put all this into practice with a numerical example. Problem: a cell has an EMF of 12 volts, internal resistance of 1 ohm, and it is connected to a 5 ohm resistor. What are the current, terminal voltage, and power dissipated? Step 1. Total resistance equals R plus R, that's 5 plus 1, which equals 6 ohms. Step 2. Current, I, equals epsilon divided by total resistance. So, I is equal to 12 volts divided by 6 ohms is equal to 2 amperes. Step 3. Terminal voltage, capital V, equals current times resistance. That is, V is equal to 2 amperes times 5 ohms is equal to 10 volts. Step 4. Power delivered to the resistor is current squared times resistance. P is equal to I squared times R is equal to 2 squared times 5 is equal to 4 times 5 is equal to 20 watts. So, the cell delivers 2 amperes of current and 20 watts of power to the load. But notice that the terminal voltage is less than the EMF because of internal resistance. Let's wrap up with a quick recap of the key takeaways. First, the EMF, denoted by epsilon, is the open circuit potential difference across a cell's terminals. Epsilon is equal to V sub plus V sub minus. Second, when current flows, the terminal voltage drops because of internal resistance. V is equal to epsilon minus I times R. Third, by Ohm's law, the voltage across a resistor is given by V is equal to I times R. And finally, when epsilon is much greater than I times R, we can neglect internal resistance in practical calculations. Real-life application: devices like electric vehicles and inverters require large currents. To avoid voltage losses and excessive heating, they use cells with very low internal resistance. I hope this session helped you understand what really happens inside a cell and why internal resistance matters. See you in the next topic, where we'll explore more fascinating concepts in physics.